Hello, my name is Alex Jones and I'm here to talk to you today about MethodOfLines.jl, a system for the automatic discretization of symbolically defined partial differential equations. Special thanks to the Wellcome Trust for providing funding for this project. If you want to simulate something, sooner or later you're going to come across partial differential equations. But solving PDEs is hard, right? It doesn't have to be. In this talk we'll cut to the chase. How do I copy-paste the textbook description of my PDE into Julia symbolic syntax and get a solution? MethodOfLines.jl is the answer, and in this talk we'll show you how to do it. Say you wanted to simulate how the temperature distribution on a metal rod evolves over time, here denoted by U, where the temperature at the ends of the rod are held at 0, starting from some initial temperature distribution, here denoted by f of x. Well, for that you'd need to use the heat equation. But how will we represent this in code? Here I'll show you how to do it with Modeling Toolkit and MethodOfLines. First of all, let's import some packages. Then we'll define our independent variables t and x, and our dependent variable u. Then we'll define some derivative operators, one for the first derivative in t, one for the first derivative in x, and one for the second derivative in x. Note that by raising a differential object to a power, you can represent higher order derivatives. Next, we'll define alpha as a simple floating point number 1.1. Next, we need to find a way to represent the equation in symbolic syntax. By calling our differential operators with u of t and x, we can take their derivatives in time and space respectively. Please note the use of the tilde operator in place of the equal sign, as equals is hard-coded to assignment in Julia. Next, we need to define the length of the rod. Here we've set it to 10 units long. And then we need to define the length of time over which the simulation is to run. Here we've done this using the interval object from domain sets. The length of time is 1 unit long. Then we'll define the temperature distribution at time equals 0, or the initial condition. Here this is 2 Gaussian pulses, each centered at 4 units along the rod and 6 units along the rod. This is done again in very natural syntax. Next we need our boundary conditions, one for the left end of the rod, here, set to Dirichlet 0, and another for the right end of the rod, again set to Dirichlet 0. Finally, we want to wrap the entire system in a PDE system, specifying the independent and dependent variables along with all of the other necessary parameters. Now we want to discretize the system. We want to discretize the spatial dimensions of the system, leaving the time dimension undiscretized so that we can use it with an existing ODE solver from differentialequations.jl along with all of their excellent features. We'll do this with MethodOfLines. We'll start by defining the step size for x, dx. We'll set that to 0.1. Next we'll create the discretization. This is an object called MOL finite difference. We'll set the step size for x to dx. Supply the variable that is to be discretized not by MethodOfLines but by the solver. This is t in this case. And then optionally supply the approximation order for the central difference scheme used to discretize the second derivative. Now we'll discretize the PDE system with our discretization by calling discretize. We need to import some solvers with which to solve it. Now we'll solve the problem with an appropriate solver. In this case we're using tsit5. Next we need to retrieve the discretized versions of our symbolic variables. We'll do that by calling getDiscrete on the system and the discretization. We'll use these in plotting in a moment. Now we'll import plots with which to plot the solution of our problem, and we'll create an animation. This will animate across the time dimension of the solution. Here's the axis for x. We use this map to extract the solution for u from our sol object. We need to index it at the current time. Here we'll retrieve the symbolic discretized form of the variable u from grid. Set a limit for the plot, and some labels and titles. Finally, we'll generate the GIF from the animation object. Set it to 10 frames per second. Note that we've added this save at parameter to the solve in order to save the result at regular intervals. Now we'll run the solve. Now we have our result. As you can see, the two Gaussian peaks are diffusing into one larger bulge and then reducing over time, as expected. Great, we've just solved the heat equation. Now let's try again, starting with a different system setup. Let's try to simulate what would happen if we connected two bars of length 5 together at different temperatures. To do this, we'll create a function step of x. Since this function contains branches, we're going to need to register it in order to use it in our symbolic expressions. Now let's replace the initial condition with this. We'll also need to set the right boundary condition to be Dirichlet 1. Now let's run this. Our simulation is completed again. Let's see the results. As expected, temperature from each region is smoothly diffusing into the other. Now let's discuss some other systems that MethodOfLines can discretize. Let's say you wanted to model something that moves as well as diffuses. We can do this by adding an advection term. Derivatives of any order can be used. Indeed, there are very few caveats as to what can be used in an equation and in what form you want to cast it. See a full list of caveats on the MethodOfLines docs. We can, for example, in quite natural syntax, add a time-dependent source term. Indeed, this could be any Julia function which returns a number, as long as it's defined under the domain. The same goes for boundary conditions. These can be Neumann, Dirichlet, Robin, periodic, or even ODEs. This is an example of how you specify a Neumann boundary condition. Let's go with a periodic condition for our next solve. We'll increase the length of the simulation and run. Here's the result. As you can see, starting from a square wave, which processes across the domain, the shape smooths into something more sinusoidal and equalizes in temperature, as to be expected. But, I hear you say, surely you can't maintain this level of generality with multiple dimensions as well, multiple spatial dimensions. To which I say, try us. Here we'll add a second order differential operator in y. Now we need to expand the argument signature of u, since it's now two-dimensional. We'll do this throughout. We'll expand the diffusion term to use a 2D Laplacian rather than 1D. And added a domain for y. We'll need to include a periodic condition for y as well. We'll make sure to add the new independent variable. We'll increase the step size to reduce the point count and improve solve time. Let's do this for y as well. We'll make sure to include the step size for y in the discretization. We'll change the plot to a heat map. Or change the name of the GIF. Perhaps that step size is a little too conservative. Let's also include advection in y. Let's make sure to add a derivative operator in y. Let's also update the step function. Now we want it to be 0 when x times y is less than 5, and 1 when it's greater. Let's run this. I'll show you the solve in real time this time. There we go. This black square in the bottom left corner is an artifact of the boundary condition handling. We hold all of the corner equations at digitally 0, though they are not actually used in the true solution. This does appear to be as expected though. Great! Finally, I'll show you about parameters. Let's say we wanted to add alpha as a parameter. We might want to do this in case we wanted to rerun the solution many times with different values of alpha and didn't want to rediscretize every time. I won't actually run this again, since we've already seen the result. Create an extra parameter alpha. And we need to feed it into the PDE system. We need to give it a default value. Now, after we discretized and solved, we could create a new problem, prob2, where we remake the original problem with new parameters. Let's say we wanted alpha of 2.2 this time. That's how we do it. That would save on discretization time and speed up iterative solves. Now, creating parameters might also be useful if you wanted to do something like train a neural network to encapsulate part of your dynamics. So we wanted to capture any hidden dynamics in some data that we had. We create a neural network that takes u of t x, y, x, y, and t, and some vector of parameters. Now we can write a loss function. Let's do that down here. This is a sketch, but you get the idea. True sol will be some data that we gathered about a true solution of this equation. Perhaps this is measured data. Of course, we need to take the absolute value of this. There's our loss to be minimized. Once this is successfully trained, you might be able to perform symbolic regression to understand what extra dynamics there might be at play that your model hasn't yet captured. For more example systems of equations and further usage instructions, please see the Method of Lines docs, linked from our GitHub page. So, what's going on under the hood? We're essentially taking your system of PDEs and turning it into a much larger system of ODEs by symbolically pattern matching spatial derivative terms and replacing them with appropriate finite difference approximations at each interior point. Then we do similar for the boundary condition equations at each boundary point. The way we do this is to create an array of symbolic variables, u1 through 10, for example, if we were discretizing into 10 steps, to represent the discretized form of the variable u. Then, for example, at index 5 for the heat equation, we would take the spatial derivative term in x here and replace it with its centered finite difference approximation, shown here. Likewise, for the term in the ODE, we replace it with the symbolic variable at that point. Thus we have an ODE for index 5. Repeat for all indices, and we'll have all ODEs necessary to approximate the PDE. What this means in practice is to generate a bunch of rules using the @rule macro from symbolic utils to match each derivative term that we want to replace. We then substitute these rules into the PDE to generate the ODE at that interior point. The end goal of all of this is to generate a symbolic system of ODEs that can be used with Symbolic's build function to generate a performance semi-discretization, analogous to the one shown here. Currently implemented finite difference schemes are shown here. We have the centered difference scheme, the upwind difference scheme, including automatic upwinding depending on the coefficient sign, nonlinear Laplacian scheme, this f of x can really be any symbolic expression, and the spherical Laplacian scheme, which is good for discretizing terms such as this one. Some features which haven't been showcased here are that it's possible to solve systems of multiple variables and multiple PDEs or other equations, that it's possible to have an arbitrary number of spatial dimensions per equation, it's possible to have equations with differing arguments, that is to say one equation could be a PDE, another could be an ODE, another could be a PDE with a different dimensionality, and it's possible to mix these arguments between equations as well. It's possible to solve steady-state equations with no time dependence. There's support for non-uniform rectilinear grids and arbitrary curvilinear grids via a change of variables. On to planned features for the future. A current limitation is that discretization and compile times increase quite considerably with increasing point count. There are plans in the works to reduce this to order 1 via the stencil interfaces that Shashi Gowda is currently working on. These will also provide quite natural syntax to specify new finite difference schemes, should simplify the implementation of further schemes in the future. We have plans to introduce conservative schemes for advection, more exotic grids, and pseudospectral methods. Lastly here, a bit of a call for assistance. While our system is quite general, and our testing quite comprehensive, it is by no means exhaustive. Therefore I invite you to try as many different varied systems of equations as possible to see where those edge cases lie, and to help us improve our package. Further, if you have any ideas for improvements, such as new finite difference schemes, finite volume schemes, or any other ideas, please post an issue. We'll be happy to hear it. I'd like to acknowledge the work of Christopher Corcus, Yingbo Ma, Shashi Gowda, Samuel Isaacson, and many others who've contributed to the dependencies on which Method of Lines is based. Further, I'd like to thank Chris again, Valentin Solzer, Emmanuel Lujan, Akash Garg, and many others who built the first stages of this package while it was still in diffec operators. I'd like to also thank all of the contributors to Method of Lines, and many of the people who've assisted me in my own work on this package, many of whom have already been mentioned. Lastly, I'd like to thank the Wellcome Trust again for providing funding. If you have any usage questions at all, any ideas, or want to contribute, please post an issue, message on the Slack, or reach out on the discourse. And if you do anything interesting with MethodOfLines.jl, please do let us know. We'd love to hear about it. So, that's all for today's talk. Thank you very much for watching and for your interest in this package. I look forward to hearing from you on the GitHub, Slack, or Discourse soon.